Thank you, Michael, for the nice introduction. So, as said, my name is Teresa. I'm from Ulm University, and I'm going to talk about our design space for gaze interaction on head-mounted displays. Future AR and VR HMDs are expected to have eye tracking as an integral part of the device. As you can see on the slide, there are already a few examples of devices that have eye tracking integrated. And the question is, why do we want to have eye tracking with HMDs? What can we use it for, and what are the benefits? So in our literature review, we've found two basic areas where eye tracking is applied for HMDs, and the first one is eye tracking as an additional explicit interaction modality. So we can use eye tracking additionally to a different interaction modality like controller or gesture. And one example was presented at last year's CAI by Kite et al., where gaze was used to indicate where the user wants to interact, and then the action was refined using the controller. The second part, or the second area where eye tracking is useful for HMDs, is that eye tracking has the potential to address unique challenges of HMDs. The most prominent example for this is foveated rendering, meaning that we adapt the content on a display to the visual perception. So we only render the part sharply where the user is actually looking at and blur out the rest. So one example here was presented by Patney et al., and you can see the part where, with the yellow circle, is where the user is looking at, and the part around that is blurred out. So what we ask ourselves is that all? And these two examples I just showed point towards the beneficial combination of eye tracking and HMDs. And the solutions that have been proposed are more or less being classifiable into those two examples I just presented. But we found that these two examples are only examples of a much bigger design space which hasn't yet been explored. So the question is, why hasn't it yet been explored? Why haven't we found more solutions? And our assumption is that we assume that it is related to the view of point that eye tracking researchers or eye-based interaction researchers had or have on gaze. Most probably, this relates to our main interaction devices, which are still the smartphones, smartwatch, and ambient displays. And in this case, gaze is treated as a 2D construct on a two-dimensional screen. However, with these new devices, with these new HMDs, we are able to create whole new three-dimensional worlds, or augment the existing 3D world with information at different depth levels. So we should consider gaze also as a 3D construct, somewhere between the physical and the virtual worlds we create with those devices. So how should we think about gaze interaction and HMDs to explore further possible solutions? And design space has been shown to be a suitable tool in HCI to systematically analyze the combination of new technologies. And in our case, we therefore created a design space to analyze the combination of HMDs and gaze interaction. And our design space is intentionally directed towards non-expert content creators. So we want to give a basic framework on how to think about those two technologies, how to think about gaze interaction and HMDs for everybody, so to say. So you don't have to have an expert background in HMD technology or in eye tracking. So in the following, I'm going to present the design space. It was created using a morphological analysis. However, I will skip the method part, like the more detailed part, so please have a look at the paper if you're interested in the method we came up with. And basically, our design space is made up by two dimensions, which are technical properties of HMDs and properties of human depth perception, which are the two components that establish the interactive system, right? So we have the HMD on the one hand side, and then we have the human part on the other hand. Starting with the first dimension, which is technical properties of HMDs. So this is basically what kind of parameters can we find in literature to describe HMDs. And we found three main parameters, which are display type, device type, and world knowledge, which we found by literature review of classifications and taxonomies of HMDs. So we have device type, which is split into AR and VR. Then we have display type, which is split into monoscopic and stereoscopic displays. And we have world knowledge, which is split into full and non-world knowledge. And the third parameter is based on Milgram et al.'s definition of the extent of world knowledge, which is the continuum. However, we reduced it here due to reduced complexity and to make the design space more applicable to do only 2 values. So in our case, none, of course, means not having any information about the world. And full world knowledge means in VR that we have always, in VR we have always full world knowledge because we created a world we designed. And in AR, full world knowledge refers to having a 3D mesh of the environment and information about the augmented data, which is put on top of it. So if we now combine all the values of the parameters, we get 8 rows for the first dimension. The next dimension, or the second dimension, is properties of human depth perception. And here we were interested in how can we actually measure where a person is looking at in space. So what's the physical response our eyes actually do if we look at something in space, and how can we measure that? And basically we have 2 oculomotor depth cues, which are vergence and accommodation. Vergence hereby describes the simultaneous inward rotation of the eyes to locate a certain object of interest on the fovea, and accommodation refers to the alteration of the lens to keep that object of interest on the fovea. When we measure that, what do we get? On the left-hand side, we get, for vergence, we get a 3D gaze point in somewhere in space. Basically, this is intersecting the 2 gaze rays. And for this, we need both eyes, so this is a binocular gaze cue, depth cue. And for accommodation, it's enough to measure only one eye, therefore it's a monocular depth cue, because for healthy eyes, the lens in both eyes alterate equally if you focus or accommodate to something in depth. So on the left side, we get a 3D gaze point, and on the right side, we get a gaze depth plane. Taken together, or taking those, putting those into parameters, we have oculomotor depth cue and ocularity. Oculomotor depth cue is split into vergence and accommodation, and ocularity is split into monocular and binocular. Again, if we now combine all the values, we get 4 columns, which make up the second dimension. Now, if we take everything together, we get this for dimension 1 and dimension 2. And as you can see, it's already a bit complex. So what we did is we reduced the parameters to binary values. Mainly we did this because we wanted to make the design space applicable in practice. But if you want to use the design space for your research, you are very welcome to define your own parameters or additional values, whatever you might be interested in. So our main contribution is actually to offer the approach and the guideline to how can we think about this problem and not the concrete content. Okay, so if we combine now everything together, we get a 4x8 matrix. And now the next step of a morphological analysis is to delete the cells that don't make sense or that are not relevant for our definition of the problem space. And in our case, monoscopic VR headset, for example, doesn't make sense in this problem space, because then you would have like half virtual world and half real world. So if you delete those cells, we get a 3x5 matrix, which is the final design space. And now to the more practical part. So how do we actually use this design space? What can we do with it? And we propose 2 usage techniques, where the first one, the classification technique, is a top-down approach, and the second one, the ideation tool, is a bottom-up approach. The first one focuses on the content that can be put into the space, or that can be classified into the space. And in the following, I'm going to show some examples, starting with the HoloLens with an additional binocular eye-tracking add-on. So we could put this, on the human part, we could put this into binocular vergence measurement, and then within the HMD part, we can put this in the cell of a stereoscopic AR display having full world knowledge in our definition. We can also put other prototypes in there. For example, IVR, which was presented by Geiselhart et al. This is a VR headset with a monocular eye tracker. And then we could also, for example, put Colliaris et al.'s work into the design space where they attached an auto refractor to a VR HMD, which means it's a device that can measure accommodation. So what I want to show here is we can, of course, put a lot of examples in here, and we can also put different kinds of content in there. Here I only presented devices, but we could also use applications or interaction possibilities. And what I want to show is that we can use the design space to indicate promising families of solutions by heavily populated cells, but also we can also identify a possible lack of solutions by empty cells or a cluster of empty cells. So this was the first technique. The second technique is a more bottom-up approach. It is, we call it ideation tool. And here again, to remind you, we treat gaze as a 3D construct between the physical and the virtual world. So what I'm going to show you are some examples, and on the left side I'm going to show the design space, on the right side I'm going to show the concept I'm talking about. Starting with versions. So how can we actually measure 3D gaze? As I said before, we could, for example, use binocular eye tracking, and then we would get a 3D gaze point somewhere in space. So now you can see on the right side, if we would use 2D eye tracking, then the upper and the image on the bottom would result in the same two-dimensional gaze point on the plane. But in space, these are really different. So binocular vergence measurement adds the depth value to the gaze point. Now, if we take the left side now into consideration, and in this example, we took a stereoscopic AR display with full world knowledge, again, which could be the HoloLens, for example. What we get is we get information about the physical and the virtual content now. So now if we look at the intersection of both of the column and the row, what we get is that we can defer whether the person is looking at virtual content or looking at physical content, for example. And one example, what we could do with it is we can fade out, for example, the virtual content once we realize that a person is looking at something physical. And then if we realize that the person wants to interact with the virtual content again, we display it, we fade it in again. So we can switch between those two. And now the state of the art is that the augmented content is attached to a wall or floating in between, but not really adapted to the point where the user is actually looking at. Another example could be that we can not only display virtual content in front of a physical object, but also behind a physical object, like a wall, for example. One example we implemented is, or what we ask ourselves is, could we now display something behind the wall, something the user is not able to see in the real world? So can we create a system that allows the user kind of to exceed physical limitations and to kind of look through walls, to scan through a wall? And of course, per se, this is not possible because it's also not possible to look at something you cannot see. So you cannot focus on empty space or behind something. But what we did is we displayed some virtual content, some gaze guiding pattern, to enable the user to actually perform eye movements that wouldn't be able without this pattern. And as such, we can guide the user to actually look behind the wall. So I'm going to show you a video. We call this application XRay-Vision. So now the person is looking at the wall, and you see the pattern. Now, if the person focuses behind the wall, we can see content that lies behind the wall. In our case, it was a beach. And then when the person converges the eyes again, the content disappears, and the person sees the wall. And now the content behind the wall again. So what you saw here are these gaze patterns which lie both in front of and behind the wall, and we are able to display this because we're using a stereoscopic AR display. So we can now kind of allow the user to do something to exceed physical boundaries. Okay, the example I showed was vergence-based, but we could also imagine that at some point we can measure accommodation. I mean, we can already measure accommodation, but not in this place. So what we would get is now the same, but with the depth layer and not a point in space. So now we can add again information about physical virtual content. If you look at the intersection, we can again differ between real and virtual content. And now what our design space does is now we can actually see alternative solutions for the same interaction possibility. So of course, I've only shown examples now, so please refer to the paper. There are a lot of more examples in it. What we did, we provided a design space intended to serve as a basic framework to guide people into how to think about gaze interaction HMDs. I presented 2 techniques here, one to classify content, one to derive new ideas or new combinations. In the paper there's a lot more about the usage techniques and also about different content types and different perspectives. So thank you very much. Happy to take your questions now.
So the same procedure as before. We have microphones down here. 1, 2, 3, 4. I'm going to ask you one. I was attending the workshop and on social head-mounted displays and missing you there in the sense that it would have been great to have you there because we proposed the one thing that you eliminated from your design space, which is a very early prototype of a head-mounted display that only has a monocular vision. And as an expert in eye tracking, I was like, we haven't fully explored that concept. But you really radically erased it from the design space, and you said to me today that this doesn't make any sense. So, how would you approach that? Like,
so, are you referring to a VR?
So we took a cardboard.
Ah, okay.
Cut it in half. Put the smartphone this way, and experimented that way because we want to be able to interact in a more immersed view than AR and also have quick access to the real world.
Actually, that sounds interesting, and I'm curious how it felt, because I think one problem you could get is that you don't get one gaze point, but somehow you get one for the right eye in the virtual world and then one for the left eye maybe in the real world. And I cannot really imagine how you would perceive that. So what do we actually measure? I don't know, gaze is defined to have one gaze point where the 2 points intersect, right? So this might be difficult too.
Yeah, it was tiring very quickly, but thanks. All right, so we have a second question there.
Hi, very nice work. The example you showed of the using vergence to allow the user to peer through the wall, that's really cool, but it's hard to imagine. Is it difficult for people to do that if there's to peer past a solid object?
Yes, so I think no one in our lab, at least, could perform this action without any guiding patterns. So what we did is we used the HoloLens and displayed a grid of points at different depth levels, and some of them, like the half of them, were before the wall and in front of the wall, and half of them, displayed behind the wall, and then you're actually able to perform this movement. And then you're able to perform this divergent movement, because, for example, convergent movement is a little bit easier to perform. Yeah, you can do like this, but to diverge your eyes intentionally is really hard. So we needed this pattern to actually do it. Yeah.
Thank you.
Thank you. MC over here. Speaking of the divergence and convergence, for some people, they have issues with this. Their phorias, aphoria, dysphoria. And I'm wondering, were you able to pre-check for these issues before you did the exploration of how people responded, just to see if that was having an effect?
We tried it out with 4 or 5 people, and they didn't have any issues, so we didn't measure that yet. Okay. That's a good point, maybe in future.
Yeah, isophoria, exophoria, really easy to check for, and it would be awesome to actually see if this was a way of helping people back from that too.
Yeah, definitely. Right. So what I'm really interested in is how can we adapt this? How can we use HMDs to actually help users improve their vision, or maybe improve not their vision, but their visual limitations, like you said. Yeah. Thanks.